Okay. So what did you notice, Nick?
For every increase on the x-axis.
Okay, so as time increases, the tuition and fees increase. Okay, sure. Other things you noticed? Yeah, Catherine, right? Okay, Catherine. The change between what and what? The change between time measured in the years after 2000, let's say, that's how we're going to measure it, and the average cost of tuition and fees is not a constant rate. And to look at that, you could just do something like this. You could say, okay, number of years after 2000. And so we could just change these to be these nice simple numbers to look at, number of years. And this is what is a very typical thing to do with data that has time on the x-axis. You just pick like a reference point and you'd say number of years after that point. So when you're working on this data, it becomes very easy to input into either your GeoGebra spreadsheet or your Excel spreadsheet or your graphing calculator, whatever you might have. And then over here you have 3362. So this would be the average cost of tuition and fees in dollars. And then you would have 3487, 3725. So what Catherine said is that it's not growing. This data is growing at a constant rate, because for equal differences in the years, here's equal differences between 2 years, they're each changing by 1 year. We don't have an equal difference in the tuition in dollars. This changes by an increase of $25, whereas these two increase by how much? Well, 13 and 25 by 38, right? What is it? Oh, 125. Wait a minute. Is that right? Oh, is it 238? Yeah, 238, right? Oh, 125, right? I see. And then 238, right? Did I do that right? So you notice that the rate of change between 2000 and 2001 is different than the rate of change in tuition and fees between 2001 and 2002. If the differences between the tuition and fees and the years, if those were equal all the way up, what kind of picture would I have? If they were exactly the same from 1 year to the next. Linear, right? Straight line. Okay. So that's what Catherine notices. It's not exactly a straight line. It's the rate of change is not constant. What else could you say? Yep. Remind me your name? Jasper. Yeah. All right. So the largest increase or the most significant change is how Jasper says it. The most significant change in the average tuition and fees occurred between 2003 and 2004, and that change was how much? On average, $613, right? So here we're changing by 125, and then 238, and then we have this huge jump. Yep. Yes. So as time passes, that's very similar to what Nick said. As time passes, tuition and fees increase. Okay. All right. So do you all agree we have an increasing trend going on? Yeah. Okay. It's an increasing trend. So that's another way we might say it's an increasing trend. All right. Okay. So what does this kind of symbol, my other class calls it the squiggle, what does that symbol mean? Does anybody know? Yeah, Nick? Right. We usually start in axes at 0, and this is not starting at 0, it's starting at 3000. So anytime you start a graph with your scale not at 0, you put this little indication that to note to the reader or the person observing the data or your bar graph or whatever your kind of graph you have, that you're not starting at zero. All right, you're all students in public higher education. One of the things that we can do with mathematics is we can start to try to answer questions we might have about time and the average cost of tuition and fees at public four-year schools. What kind of question might you have in the back of your mind, Ken?
What justifies the cost?
Right, so that's what someone else says is what justifies the cost increase, okay? That's one, particularly if you're a parent paying for your kids, what justifies the cost increase. But also, if you're not a parent and you're paying for your own education, you might like to know that. Yeah. Oh yeah. In this fact, this graph this has been adjusted for inflation. So that means any increase that's great. Let's see. If it wasn't adjusted, how does this go? Oh, my economics. What does it mean when it's adjusted? So any change, any difference you see is not due to inflation. It's due to actual real change in cost. Okay, because it's been adjusted for inflation. Yeah. And so say what you said again so I can write it down. The rise in cost of tuition and fees consistent with inflation. All right, so this is the average cost of tuition and fees for public four-year schools. What might you be interested in in a couple of years? Nick?
How much is my cost go up over the course of my?
Right, so what's it going to cost me in a couple of years on average, right? So how much will I be paying? Now this only goes to 2010, so how much will I be paying for a four-year college, if public college? And let's say we're going to pick in 2018. That might be nice to know, okay? Now that question we can answer today, or we can predict or estimate today. A question like number one has a lot of different pieces that go to it. You'd have to look at number one, whatever country you're in this case, the United States, maybe the state, or what's happening in different parts of the country, socially, what's happening socially in terms of wages. You also have to look at state support if they're public institutions. You'd have to look at historical things. Did something happen between 2003 and 4 that would cause, was there some type of recession? There's lots of things. In order to, again, look at that, you would be looking at a different kind of mathematical test, which would be something in statistics called multiple regression. You'd want to know what are the factors that really contribute and make the difference between the average cost of tuition and fees. Yep, Jasper? Right, right. Right. That's right. That's right. Fees have continued to go up as one of the reasons that the first jump happened was the state used to support us at a very high percentage, and now it's less than 50%. So as the state contribution to the community colleges anyway, I can speak to, but really it's all of public higher ed has decreased, the fees have increased. So when I get a tuition waiver for my kids to take a course here, it's waiving $26 a credit, right? But not the fees. So it's kind of, it's a benefit, but it's not a huge one. So let's take a look at how we would go about asking questions similar to the last one, because that we can get a hold of, whether it's an accurate model or not depends on a lot of things. So start us off with number one here, Stephen. So the two quantities we're interested in here is the average cost of tuition and fees, which we're representing with the variable t, and the number of years after 2000, which we're representing with the variable x. We're interested in the relationship between those two variables, and can we find a mathematical model that will represent this data well? So what I did is I took GeoGebra before you came in here, and I put in the data that you have in front of you. Hurry up, open up. So you can see on the side here, I defined each of the years as the x variable using the definition years after 2000. So 2000 would have the number 0. It's 0 years after 2000. 2001 would be 1. And then here is the tuition and fees for each of those years, which you can find on each of the tops of your bars, right? So each of these points here, A, B, C, D, up to K, represents this ordered pair. These represent the actual year and the actual tuition and fees. This green line is a model, is modeling, it's an equation. I put an equation in here to try and find a way to get some type of line or parabola or some kind of polynomial equation to get as close to those actual points as possible. So we may have said, well, that line shows a linear trend as one of the variables increases, the other increases. It's not exactly linear, but if you notice, I'm going to just take this little four-way arrow up here, and I'm just going to move this and move my scales together, and you can actually see what kind of equation or what kind of shape is that I'm using to model this parabola or a quadratic. So I'm actually using a quadratic equation to model this, because I could also use a linear equation which would look like that. And here's the linear equation. This is the equation you're going to be working with in your project, is a straight line. And you can see they're both really close. And it's only when you actually spread the data out that you can see some of the differences between the two models. And the quadratic model actually fits this data the closest. But you can see there's very little difference between the red line and the green portion of the parabola. Okay, so both are good models in terms of estimating and perhaps making predictions. So we're going to work right now, we're choosing to work with this model, which is a quadratic equation. And we know the shape of that is the overall shape is a parabola. So let's see if we can answer this first question. Let's use this model, which we're calling a formula. Use the formula or use the model. You could have either one of those words to find the average cost of tuition, which means I'm trying to solve for t. Solve for t, that's what I'm trying to do. To find the average cost of tuition at public U.S. colleges for the year ending in 2010. So I'm trying to use this model now to make an estimate. So I'm trying to estimate the cost in 2010. Okay, so you might say, why am I doing that? Because I actually know the cost is $7,020, but it's helping you get used to working with the types of questions you can ask and using a model. So someone other than Nick and Jasper, who's made some contributions today, want to tell me how I would begin this problem. What do you need to do? Yeah. All right, so I have to figure out what x is, right? So how do I figure out what x is? What would I do, or what does my brain do? What do you actually do, what operation to find the value for x? You subtract. And what do you subtract? 2010, take away 2000, and we know that's a 10-year, 2010 is 10 years after the year 2000. So that's the value we're going to substitute for x, and once we do that, we'll get a value for t. So we're going to now use the formula to estimate t, And you know, folks, I do this. This is a little thing from statistics. I put a little hat over that variable to remind me that I'm estimating. I'm not getting the exact answer. So I always put the little hat that reminds me I'm finding an estimate or a prediction. Right? So t equals 4 times 10, because x is 10, squared, plus 341 times 10, plus 3,194. So my estimate comes out to be 7,004. The estimate for t. When I do all that mathematics, it will come out to be 7,004. So if I were answering this on a project, if I was finding this answer and then writing a sentence to describe it, what's really important is that you recognize that 7,004 is an estimate. It's not the actual tuition average of tuition and fees for that year. So I would make sure any sentence I write uses the word estimate or a prediction if I'm going into the future. So I would do something like this. In 2010, there's 1,000 ways to write this sentence. I'm just picking one. We estimate that the average tuition and fees at public four-year colleges will be 7,004, and you put on your unit of dollars. Okay? So the key here is somewhere along there, you talk about it being an estimate. All right? So you want to make yourself a little note here. Say, remember this for my project. Okay? What about this estimate? Does it underestimate or overestimate the actual cost that we saw in the bar graph for 2010? It underestimates because the actual cost in the bar graph was that point, 2010, $7,020. So it's an underestimate, and it underestimates it by $16. So it underestimates the average cost of tuition and fees for 2010 by $16. All right. So let's use this model to predict the average cost in tuition and fees at colleges ending in 2014, in the year ending 2014. And I would like tables 1, 2, and this half of table 3 right here from Kenneth to, what's your name?
Jenna.
Jenna. From Kenneth to Jenna to do the first one. And I would like names. Molly, Mahendra. So from Molly, the M&Ms through table 5, okay, to do 1990. When you get your answer, put up your flag and make sure you check with your other tables to make sure you're in agreement. All right, so someone from table 1 or 2, or Kenneth, Jenna, or last one, would you like to tell me what you used for your value of X? Yeah? 14. And you get that by taking the year that you're interested in and subtracting 2,000 from it. And you get a positive 14 because it says that it's 14 years into the future, beyond the year 2000, right? If it's positive, you're looking at years into the future, okay? And when you put that value of 14 into your model, what do you come up with for your estimate for T? $8,752. That sounds great. Do we have agreement on that? Okay, good. Okay, 1990 is a little different. You still start off with 1990, and when you subtract 2,000 from it, you get what kind of number? A negative 10, because it actually indicates that you were 10 years prior to 2000. So the negative number talks about past tuition and fees. And then you put a negative 10 in where you see X. And what do you come up with for your answer for the average tuition and fees for 1990? Yeah? Go ahead. Eula? 184, right. Okay, so does the prediction for the year ending in 1990 seem plausible? No. I know. Well, actually, if we went back a few years, it would have been negative, right? We can actually find when it would have been 0 using the model. So no, it doesn't seem plausible. Okay, so this is an important statement right here. You might need it for your project. Sometimes a model, if it's extended too far beyond your data set, either too far into the future or too far into the past, this is called extrapolation. That's the word we use, extrapolation. So when you go out extra into time, you can get estimates that do not make sense or are unreasonable. In these situations, we say we have model breakdown. The model is not good to use in the future or the past. Now, just think about if we were looking at data for prices of gasoline at the pumps from 2010 to, or say 2008 to 2012 or 13. Would you see an increasing trend like we just saw? No, no, I'm saying in those years. Would you see an increasing trend? Was gas going up every year pretty much, right? So if you were then trying to predict 2016 gas prices using that trend, how accurate would it be? Way off, right? Because they've come down. Okay, so you've got to be careful using these models when you go beyond your data range. You just got to be careful about making too many statements. Okay, so, and here's some actual information right here about the costs between the average tuition and fees at four-year private and four-year public for your knowledge, okay? Just for you to have. All right, so sets is the last thing we're going to talk about. And then you're going to have, I hope, a good 25 minutes to work on your class activities today. So someone want to read a set for me? Taylor?
A set is just a collection of puppets. For example, you have a set of a set of puppets, or a set of hospitals.
Okay. 6. Jonathan? Right. So if you have a set where you have a finite number of members or elements, then you just literally list them with a comma in between them. But what's most important is every time you want to talk about a set and you're listing stuff, you must include those curly braces or else you're not giving me a set. So if you were to list, if I ask you for a set on your take-home quiz that I give you on February 8th, and you correctly list the members of the set or the elements, but you don't use the curly braces, then that's not a set. So you must have these curly braces because it says, hey, I'm a set. That's what those curly braces mean. Okay, so if I asked you to let capital A represent the set of the Three Stooges, then you could say A is equal to curly braces, Larry, Moe, and Curly. Okay, and that's how I would represent that set. So now I'm going to ask you at your seats, and between all of you, I know you can come up with this. Let B represent the set of the 4 Beatles that arrived at JFK in 1964. And here's their pictures right here. If you're too young or you know nothing about the Beatles, talk to someone. All right, so we've got the Beatles. Now we're going to talk about really 3 ways to represent a number set, because numbers are often, to represent numbers, they're an infinite set, and we can't list every possible number, right? So we have to have several ways to represent numbers. So the 3 ways we're going to use today, one of them is called set builder notation. The other way is called interval notation, which is what your MyMathLab uses. So when you write a set of numbers in MyMathLab, you'll be getting lots of practice with interval. And then the other way is the real number line. So we're going to show you how to go back and forth between these 3 representations of sets of numbers. So set builder kind of looks a little funky and a little scary when you first look at it, but it's not that bad. It's just got a lot of little things you got to learn how to say and read. So A set builder notation is a descriptive way to write a set. It's almost like writing in a sentence. Sometimes those sentences can be in the form of equations or inequalities, but you're describing how you get to be a member of that set. So generally speaking, when we use set notation, we start with our curly braces and end with our curly braces. We usually put some type of variable to represent the number, so x is kind of popular. Then we have this straight line, which is read as such that, and that's all written down here. And then we say x has to meet some condition that we could actually say is true or false, because I need to know what number gets to be in that set. So if it meets the condition, it goes in the set. If it doesn't meet the condition, it doesn't go in the set. Okay? So for example, if I wrote this, curly braces x such that x is greater than 2, I would know what numbers go into that set and what numbers don't go into that set. I couldn't list them with the roster method, but I would have a clear understanding of whether a number belongs in that set or not. Okay, so if I were to represent this with the number line, it would look like this. I'd be at 2, and that's why I have all the colored pencils at your desk. I would then shade from 2 all the way to the right with an arrow saying that I'm going from 2 all the way to positive infinity, but I'm not including 2, so I use a parenthesis to say I'm not including 2. So that's how I would use a real number line to represent that set of numbers. If I wanted to represent the set of numbers that said x greater than or equal to 5, then I would do a similar thing. I would draw a number line, I would put a 5, and I would shade everything to the right of 5. But this time, when you use a staple, look at the shape of a staple. A staple looks a little bit like a bracket. You want to include it, you use a bracket like this to say I'm including the 5 because of that equal sign right there. So when you're including the number, or the in this case we call 5 the end point, you put a staple or a bracket. When you don't include it, you use parentheses. All right. Now that's set builder notation in the real number line. Yep.
Did it used to be like an open circle?
Yes. Yeah. But we're not using circles here just because this is what your book uses for notation. And that's what you use when you now go into interval notation. So you want to be consistent. Ramses? Okay. So now the final notation is called interval notation. So to represent this set of numbers with interval notation, it looks like this. Okay. So you have 2 because that's where you're starting. It's your smallest number in this set. 2 is the absolute smallest number. You have the parenthesis because 2 is not being included. It's all numbers bigger than 2. And then you're going out to positive infinity. You're going to the right. You never can enclose infinity because it's not a number. It's a concept, right? So do not think that the next number in this set is 3. I asked people what numbers are in this set. 3, 4, 5. I said, any other numbers? Well, 6, 7, 8. Any other numbers? Well, you know, those are integers. You have a zillion numbers right after 2. 2.000000001. You're looking at all numbers. That's why you shade it. Okay? So you never include you never use parentheses, the staple mark, the bracket when you're looking at either positive or negative infinity. And so let's take a look at these 2 number lines right now and see if we could represent the sets of numbers both using interval notation and set builder notation. Let's see how we can do. Does anybody want to take on the first one with interval notation? Okay, remind me. Oh, Eula. Bracket. Yeah. Comma, 4. Yeah. Right. You notice that if you look at the number line, you know what to write in your interval notation because you're either going to see a bracket or you're going to see a parenthesis, right? It helps you out. All right. Now, set builder notation is curly braces, the set of all x, such that, now how do I write all of those numbers between and including -1 and 4? What kind of statement do I make here? Yeah? Yeah. Yeah, so x has to be in between -1 and 4, and so that's where I use my inequality symbols. Okay, so x, you cover up the left-hand side with your hand like I'm doing, and you say x has got to be less than or equal to 4, right? Then you cover up the right-hand side and say, oh, x, and then you read right to left, x is greater than or equal to -1. And that describes that set with set builder notation. Okay, notice in interval notation, -1 is smaller than 4, so that's always the first number that's listed in the interval notation. Okay, who wants to try interval notation for the second set, other than Nick? Anybody feeling brave? Even if you're not brave and you're just willing to give it a shot, it's okay. Remember what we learned, Euler, in art yesterday? Art is a series of mistakes. Remember that message about making mistakes leading to solutions? Wasn't that beautiful? I should show that in here, don't you think? Yeah. Okay, now let's see. It's something like Elisa. No, it's oh, good, Elise. I was close. All right.
So would it be bracket negative
Okay.
comma 1?
Almost. Okay. Do we have any editors in here? Does anybody want to edit? Yeah. Last one. Yeah. Erase the bracket on the infinity. Okay, -infinity, and what should I put there? Parenthesis, right. So you use a parenthesis anytime, right here. Why do you think we use a symbol for infinity in the position? Why use a parenthesis? Always parentheses with infinity or negative infinity. So good, Elise. Thank you for being brave. Yep. Because, no, that's a bracket because 1's in the set. So 1 gets to be in there. You know, 1 isn't the loneliest number anymore. 3 Dog Night. Check that out. All right. All right. And who wants to try set builder notation? Last one, you want to try that? Okay. Curly braces x such that like this? Oh. No. X greater than to what? Okay. X greater than or equal to 1 goes that way.
So would it be?
Give last one a chance. Yeah, go ahead. Last one. Less than to 1. Right. Perfect. So all the numbers less than or equal to 1. You've got 20 minutes or so to work on your class activities. Have fun. Anybody want a music request for Pandora?